In 1905, Einstein invented his special theory of relativity to explain the results of the Michelson-Morley experiment, which seemed to have ruled out the existence of the ether. In Newton's time, light was known to be a wave, and like every other wave, had a medium of propagation, which was called the luminiferous ether. The ether was thought of as a transparent medium that permeated the whole of space, and oscillations in this medium were the EM waves. The ether theory, even today, seems to be the most plausible theory of electromagnetism because one can use it to explain unnaturally observed phenomena such as the constancy of the speed of light, dark matter, gravitational waves, and so on. Let us assume that the ether theory is correct just for a second. That is, light and other EM waves are oscillations in the ether just like water waves are oscillations on water surfaces. We know that for a stationary, homogeneous liquid, the wave speed on its surface is constant. However, from the wave formula C equal lambda f, the wavelength and frequency must be adjusted in order for a constant speed to be maintained. On the ether, which we have assumed is the medium for light, these changing wavelengths and frequencies correspond to different EM waves, all traveling at speed c. Here, the ether theory is consistent with the electromagnetic theory and the constancy of the speed of light, but not as assumed by Einstein. Just like any other wave, this medium has to be triggered by the movement of something through it. For a water surface, the trigger could be dropping a stone or touching the surface with the finger. For the ether, the trigger is the movement of mass or charge. We know that accelerating charges produce EM waves, and thanks to general relativity, we now know that accelerating masses produce gravitational waves. With the ether theory, the propagation of gravitational waves can be explained the same way, and we can have a whole spectrum of these waves like we do for EM waves. Another thing that the ether theory can explain perfectly is dark matter. This theory directly informs us that empty space is not really empty, but filled with the ether, which is a medium and, like every other medium, has mass. Since it is transparent, we cannot see this extra mass, and this is consistent with the description of dark matter. I have already made a very elaborate explanation of this dark matter theory in this video, and also calculated the density of this dark matter as a function of the Planck's constant. I used the value of this density and the volume of our Milky Way galaxy to calculate the actual mass of the galaxy, and the result was in perfect agreement with astronomical data. I achieved this by assuming that the ether theory is correct. I cannot emphasize more on this, so I urge you to watch the video and see the derivations for yourself. Regardless of this, the Michelson-Morley experiment claimed that the ether does not exist. I took the time to analyze this experiment in the first part of this video, Destroying Special Relativity, showing where they made an error with the calculation, which is why they had the results they had. However, this is not the only experiment that is used to justify the correctness of special relativity. The first direct test of special relativity was the Mu-meson experiment used to test time dilation, a consequence of special relativity. In this video, we will be looking at the errors of this experiment and show why the experiment cannot be correct. We shall have a quick recap on time dilation to help the understanding of this experiment, but if you want to dive directly into the experiment, you can skip this recap. Time dilation is the difference in elapsed time as measured by two clocks, either due to a relative motion between them or a difference in gravitational potential between their locations. When unspecified, time dilation usually refers to the effect due to velocity. Consider two people trying to measure how long it takes the car to move across a path of length L. One of them is in the car and the other standing on the start line. Each of them is using an atomic clock for this experiment. At the instant where the car reaches the start line, with a constant speed v, the two clocks are synchronized. An atomic clock measures the time it takes the atom to go up and down its vertical arc. Let's assume that the time for the tick-tock of the clock is equal to 1 second. For the observer on the ground, the atoms go straight up and down. If the height of the clock is h, then the time it takes to make a tick-tock is given by t1 equal to 2h over c. That is, assuming that the atoms travel at the speed of light. Well, this is where I have the first issue, because it is not possible for atoms to attain the speed of light. But let's just ignore that. For the observer in the car, when the atom is released from the bottom of the clock vertically upwards, by the time it reaches the top would have moved a horizontal distance vt2. So the atom must trace an inclined path if it must touch the top at the exact position as the clock of the observer on the ground. The same thing happens on their way down. By Pythagoras, we have the following displacement equation. Making T2 the subject yields 2h over c times 1 over the square root of 1 minus v squared on c squared, which is equal to gamma times T1. Since v is always less than c, then gamma is always greater than 1. Therefore, it takes longer for the clock to do a tick-tock in the car than for it to do on the ground. So, for example, by the time the clock on the ground records 5 tick-tocks, which in this case is equal to 5 seconds, the clock in the car would have only recorded about 3 tick-tocks, that is 3 seconds. That's how a moving clock runs slower than a stationary one, hence time dilation. My next problem. If the atoms were emitted vertically, what then caused them to travel diagonally? I bet it gets some extra horizontal energy from the car to change the direction. And if you add this to the math, time dilation is not possible. But if they were emitted diagonally, as presumed, then this clock can no longer be compared to the stationary one because the design of one has been changed. It is claimed that this diagonal path is the path as seen by the stationary observer, but this is only true for massive particles such as a ball. When you shine a torch vertically upwards in a moving car, everyone sees the photons go vertically upwards because their motion is not affected by the motion of the car. To solve this dilemma, you can simply change the direction of motion of the car from horizontal to vertical without rotating the clocks, since passage of time should not depend on orientation. When you do that, you will see that the tick-tocks on the moving clock will be exactly the same as those on the stationary one. Again, let's ignore this and continue. Let's assume that both the ground observer and the observer in the car had an identical radioactive material with them when their clocks were synchronized. Let's say the half-life of this material is 4 seconds. When the car reaches the end of the road, both observers check their radioactive material and their clock. The person in the car at the end of the journey read 3 seconds on his clock. This means his radioactive material would not have decayed. The stationary person, however, reads 5 seconds on his clock, which means that he would have left with him only half the mass of the radioactive substance he started with. This right here is an experiment we can do to test time dilation, and it is what was tested in the Mu-meson experiment, which we are about to scrutinize. This experiment was presented by David Frisch and James Smith in the YouTube video titled Time Dilation, an Experiment with Mu-meson. So you can check the video for full details, since I shall only be showing you parts of the video that are relevant to my explanation. Don't forget to click on that subscribe button below this video so that you don't miss out on other interesting videos I will be creating to reveal loopholes in our so-called modern physics, and also answering unanswered questions such as what is dark matter and so on. Also, if you find this video informative, then help YouTube show this video to more people by clicking that like button. Anything that occurs at a constant rate can be used as a clock. For example, the tick-tock of the atomic clock we described earlier, the half-life of a radioactive substance, the oscillation of a pendulum, and so on. The Mu-meson experiment is considered a direct test of dilation. In the video I mentioned, mu-mesons raining down from the atmosphere are captured in a scintillator so that they decay, and the number of mu-mesons that decay is counted 6,000 feet above sea level and at sea level. The idea of the experiment is that if, for example, you can detect for a given area 500 mu-mesons at a significant height above sea level, then according to classical physics, you should only be able to detect only a very small number of mu-mesons at sea level, because the time it takes the mu-mesons to travel to sea level is greater than their half-life, and they would therefore decay before being able to reach sea level. But if time dilation is correct, then in the meson's reference frame, time passes slower than it does in a rest frame at sea level. So the mesons will have enough time to reach sea level without decaying, and therefore more mesons will be detected. To do the experiment, we need to first be able to detect the particles.
The mu-mesons we'll use are produced high in the atmosphere and come shooting down toward the Earth. As they come down, some of them disintegrate in flight. The number arriving at a high altitude is greater than the number surviving to reach sea level. Right now, we're up on top of a mountain, Mount Washington in New Hampshire. We will count the number of mesons that arrive here, and then we'll go down later to sea level and count the number that survive to arrive there. By comparing these numbers, we will show that these moving clocks run slow. To start, we need to detect these mu-mesons.
Every time one of those mu-mesons, which Professor Frisch has told you about, passes through this special plastic scintillator, a flash of light is emitted. In fact, the plastic is scintillating right now from the mu-mesons that are passing through it. We can't see them because those flashes are much too dim to be photographed. So we detect them with this photomultiplier, which is just an extremely sensitive photocell, which
They use something called a scintillator, which is just a piece of transparent plastic that glows when struck by these high-energy particles. The scintillator is connected to a high-speed oscilloscope, which takes the readings of the number of flashes produced. Since mesons move at high speeds, they had to slow them down to stop inside the scintillator, where they would then decay. This was achieved by placing the scintillator under a pile of iron blocks 2.5 feet. Since mesons are charged, their interaction with the charges of the metal will cause them to lose energy and slow down.
when a positive mu-meson decays, it gives off a neutrino, an antineutrino, and one positive charged particle called a positron. When the mu-meson enters our scintillator, it makes a flash of light. If it stops and decays in the scintillator, the positron makes a second flash of light. That puts a second pulse on our oscilloscope trace at the instant the mu-meson decays. So now we're ready to stop a lot more of these mu-mesons and measure the time distribution of their radioactive decays. So Dave, push the scintillator under the iron, and I'll get back to the scope. Let's have a look. You may notice that there are fewer sweeps.
When a meson first enters the scintillator, the first flash is produced due to the impact. It is now at rest. When it decays, it produces a neutrino and an antineutrino and a positron, which sets off at a high speed, producing a second flash. Therefore, by counting the number of second flashes on the oscilloscope, we can know how many rest mesons have decayed. And we can also know exactly how long it took each meson to decay after being stopped. James and David placed their setup on a mountain top 6,000 feet above sea level and left it for an hour, recording averagely 564 decays. The decay time for each meson was plotted.
So here's our finished chart, based on the 568 counts which we got during this hour.
The 568 counts we have plotted on our chart are the result of 1 hour's run. Previously, we had taken 5 different runs, each for an hour, and their average comes out 564, so that the 568 we have plotted are indeed a good sample of the number of mesons decaying in our scintillator every hour.
So you can think of the mu-mesons as coming down in a steady rain from hour to hour. Many mesons live for as long as 1 microsecond. Fewer live for 2 microseconds. By the time we get to 5 microseconds, only a small fraction of the original number remains. And by the time we get down to 8.5 microseconds, which is the longest time we can see on the scope face, only a very few mesons are decaying.
That chart is a pictorial representation of the decay times of those mesons which had stopped in the scintillator before we began to measure their decay times. They were at rest with respect to us during the time shown on the chart. Now we come to the heart of the experiment. What happens to the decay times of these mu-mesons when, instead of being at rest with respect to us, they're shooting on down by us with speeds nearly that of light? Let's look at the chart in more detail.
For instance, here's a meson which lived for 3.5 microseconds sitting in our scintillator. Suppose we hadn't stopped it. Where would it have gone? Here we are, up on top of Mount Washington, 6,300 feet above sea level. We stopped that meson up here. If we hadn't, it would have gone on for 3.5 microseconds down below before decaying. Now how far would that have been? It would have gone a distance 3.5 times 10 to the minus 6 seconds times its speed v. So in order to know just how far it would have gone before decaying, we need to know its speed v.
Fortunately, we do know the speed of the mesons which stop in our scintillator because we know how far a charged particle of a given mass and speed can go through matter. A mu-meson entering the top of the iron with 0.9950 times the speed of light gets...
So we see that if they had not stopped the mesons, they would have kept on moving for the length of time it took them to decay in the scintillator. And because those times are very short, only few of them will survive long enough to make it to ground. This means that if this same setup is placed at sea level, only about 27 mesons should be detected. However, they detected about 412 decays. By this result, it was concluded that time in the meson's frame runs slower. Hence, time dilation is true. Those are so far the essential things to be known about the experiment. Now, let us look at the error that is keeping the experiment alive. At the mountaintop, they used a 2.5 feet thick block to slow down the mesons down to zero speed. At sea level, they reduced 1 foot from the thickness of the blocks, claiming that it should compensate for the extra air molecules that the mesons from the supposed mountaintop have to travel against. This is hard to believe given that iron is far denser than air. However, science is not about what you believe, so let's talk math. The formula used to calculate the rates of energy loss when the charged mesons move through a material is called Bethe formula, and it is given as follows. Notice in this formula a very important term, the gamma factor. So in an experiment to prove special relativity, to calculate what thickness of blocks need to be removed to compensate for air, they used the special relativity gamma factor. This is circular. How can you use special relativity to prove special relativity? What they should have done instead is count the number of mesons reaching sea level without the blocks, then with the 1 foot thickness of blocks, and show that the number of mesons detected when the 1 foot block is used is half that detected when there are no blocks. That will confirm that the slowing power of the air between the sea level and the mountaintop is actually the same as the slowing power of 1 foot thickness of blocks. They should have done that instead of using special relativity to try and predict it. This is why it is called an experiment. If you use the Bethe formula, which has the relativistic gamma factor in it, to calculate the thickness of blocks that need to be removed, then in fact the result of the experiment will be consistent with special relativity, and this is hardly an experiment at all. Secondly, let's assume that the experiment is true and that time dilation is correct. Let us take a look at the experimental results. This is the graph plotted for the decay times of the mesons collected within the hour. The lines represent the lifetimes of the mesons, and the axis is given in microseconds. By looking at the plot, we can draw a line across like so, and we see that the smallest possible time that a meson in this distribution can live is 0.2 microseconds. Given that special relativity is correct, the relativistic time is equal to 0.2 times the relativistic factor 1 over the square root of v squared on a c squared. We know that the mesons travel at 0.994 the speed of light. Therefore, the relativistic time is equal to 83.6 microseconds. In this time, the mesons should travel at least 16,000 feet before decay. Therefore, we should detect the same number of decays at sea level as we will at 6,000 feet. But in the experiment, only about 400 were detected at sea level, in contrast to the 564 at the mountain top. This difference is too great to be ignored. Therefore, special relativity is not consistent with the experimental results, and hence special relativity is wrong. I have gotten a lot of comments of people saying that special relativity has been proven repeatedly in experiments and therefore it must be correct. Is this the type of experiment you are referring to? Some say the GPS will not work without it. I will do another video to show you that the GPS can and does work fine without special relativity. And I will also be doing videos to debunk other special relativity experiments. So if you feel like you want to follow up on this, then subscribe. Feel free to check the first video I made to debunk special relativity theoretically and mathematically. I am now approaching it from the experimental perspective. The link to the video is in the description below. Also, don't forget to like and drop your comments respectfully. Thanks for watching.